Hello again everyone, welcome back to ptet.chemistry channel. So in this experimental tutorial video, I'll be talking about the factors that affect rate of chemical reactions. So rate of chemical reaction is basically how fast the reaction is going. So you need to monitor how the amount of substance changes. It could be referring to how the reactant that undergo the reactions, how that changes. So that could be monitored by the changes in the mass of the reactants together with the products as they change during the reactions, especially as they react to form a gas, and gas can escape, and therefore your mass is expected to decrease over time as the reaction progresses. Another way of monitoring a reaction is when you produce a gas, you can collect the volume of the gas as well. Okay, so I've got a couple of these experimental setup behind me. I'll start off by talking about the first factor, which is to do with surface area. So let's just get started. I have got a mortar and pestle. So this is the mortar and this is the pestle. So what we're going to do is we're going to crush some solid. I've got a mass balance here as well. So what the mass balance does, this is a mass balance. A mass balance measures mass. It's called electronic mass balance. Okay, so what I have really is marble chips. So marble chipping here actually refers to calcium carbonate. Calcium carbonate, calcium 2 plus and CO3 2 minus. What you actually get is you get this formula, which is calcium carbonate. But this is the powdered form. This is actually powdered form of calcium carbonate. So it's already powdered. But this one is the marble chipping. They are solid. So we're going to investigate surface area. So I'm just going to put my beaker on top of this mass balance. And hopefully you can read that. I just press 0. 0 will do tearing, T-A-R-E, or 0 mass, it reads 0.0, taking into account the mass of the beaker there. So I'm going to take out one small piece. It reads 1.7 gram of this solid here. So I would take roughly another similar size kind of solid. So they wouldn't be exactly the same mass, but they will be very, very similar mass. When we are investigating surface area, we do not want to change any other thing. We want the factor to be exactly the same. There is 1.3, there is 2.2, that is no good. We want as close to 1.7 as possible. So what was that? Nope, there's still too much there. Just give me a minute. Let me try and get this right. I don't think I'm going to get it right. So there is around 2 gram there. Not too sure if you can see that properly. So there is around 2.0 gram. Previously, I had 1.8, 1.7. I wonder if so start from 0. So this is 2.1, 2.0, and this was also 2.0 just now. So they both have the same mass of this solid. It's important that we recognize that this marble chipping is actually calcium carbonate. So what I'm going to do is I'm going to crush one of these. Both of them have the same mass, but one of them will involve me crushing the solid using a pestle and a mortar. A mortar, you're going to crush that. So I'm going to crush that solid. That's good. As you could see now, they are the powdered crush form. This is still the lumpy, L-U-M-P-Y, the lumpy solid. This is the crushed solid. So I will have a conical flask. So in this conical flask, what I'll do is I'll put in the 2 gram of the solid. And this is calcium carbonate. So carbonate plus acid will give me a gas. So the acid I'm going to use is hydrochloric acid. Hydrochloric acid has got this formula HCl, hydrochloric acid. What I'm changing and investigating here are basically surface area. So this is a powdered solid, a much larger surface area compared to this lumpy solid that was before I crush it. They had the same mass because I don't want to change anything. I want to make sure that the mass of the solid is the same when I compare the two different experiments. When I use the acid, I must make sure that I use same volume of the acid as well, so that I'm not changing any other thing except the surface area. So this one is a measuring cylinder. Measuring cylinder measures volume of solution that is around 10 cm cube. 10 milliliter is 10 cm cube. I'm going to monitor the collection of gas. This thing here is the conical flask. It will produce a gas, the gas will escape. I want to collect the gas. So I put this thing on top there, and then this gas will pass through this tube. This is called a downward delivery technique. This is a delivery tube. So these are made of rubber. This is a delivery tube. The gas will go up there. This looks like a hole, but it's actually been sealed on the other side, so it is not going to go anywhere through this hole. It's just going to pass through the inlet there, and then I have to collect the gas. I need to measure the volume of the gas produced, so we're going to collect gas by using displacement of water. So I fill up my container, my water trout, with just water. So I'm just, filling it out with tap water. So you could use any sort of water trout that would be useful, that would be sensible, but the water level needs to be high enough because of what we're going to do after this. So this is collection of gas. Make sure you know this technique. It's a very important technique here. So what I have here is a measuring cylinder. So this is another measuring cylinder. Another measuring cylinder. This is a bigger measuring cylinder. It measures from 0 all the way to 100 milliliter, which is 100 cm cube. We're going to invert this, but at the moment there is no water inside here. There is just air that fills up the inside. So what we need to do is we need to fill up this measuring cylinder with water. So I'm going to go to my sink here, and I have to fill up this thing to the very top. So fill up your water, fill up your measuring cylinder with water to the very top. So hopefully you can see this water level is on the very top here. And this is the important technique now. The important technique is to invert it so that I don't lose anything. So I have to close up the top when it's fully filled, invert it into the water here. So you might have to do this a couple of times until you get it right. Do not lift this up all the way, because if you lift it up all the way, what happens then is all the water will come back down. You see, I've got an air bubble there, so that's not entirely ideal, but most of it is the water that fills up previously. So this is still quite a good setup, because the level essentially, it reads 0 cm cube, that it starts from the very top here. But if you have lost a bit of water, then it won't read 0, because this level will be slightly lower as you lost some water in there. I was just saying, you do not want to lower it all the way, because you need to have an inlet for you to poke this into. So I'm going to lift this up a little bit so that I can see there's a space at the bottom here. Okay, I can put my finger underneath here. So this delivery tube, the gas collection, I have to put up the hose in here. Okay? And the gas that is being produced from the conical flask. So this is the conical flask. This is the reaction here. The conical flask, this reaction, this is sealed. This is airtight rubber bunk. Conical flask, the gas produced pass through the delivery tube, and then they get collected in this measuring cylinder. Okay, this is an inverted measuring cylinder. It's got water filled up to the very top. So I'm ready to start my experiment. Remember, I have to carry out 2 experiments. My objective here is to investigate which reaction is faster using the crushed powdered marble chipping, which is calcium carbonate, or the lumpy form, which are just big pieces, which have smaller surface area, because when you have big piece, only the outside are exposed to the acid, and therefore we will see how fast it is. Okay, so we could see how much volume of gas get produced after some time. So being a rate of reaction experiment, you do need a stopwatch. Let me see if I can get this to work. Can't get that to work. Nope, something is wrong with this stopwatch. This is probably a better stopwatch. This is called a stopwatch. So a stopwatch measures time. In a rate of reaction experiment, you want to monitor how much changes over time. I'm doing a collection of gas. I want to see how much gas get produced, how much gas is collected after a fixed time, comparing the lumpy form versus the crushed powder form. Another way is to monitor the time for a fixed volume to be produced. Okay, so I will start timing only after I add in the acid. I need to make sure that I use the same volume of acid for both my experiments. Every other factors must be kept constant. Things like temperature, things like volume of the acid, concentration of the acid, what else? The mass of the solid, everything else must be kept constant except for the surface area of the solid. Okay, so observe what happened to this measuring cylinder here. Let me just move that slightly further apart, not too sure how well that will appear. So the job really is put in the acid and then monitor what happened to the gas here. Okay, so I'll pour in the acid, and the moment I pour in the acid, then I'm going to seal it immediately. As you could see, there is fizziness. So it's fizzing. Not very clear actually. So it is fizzing. And what you could also see is there is bubbling. So there is bubbling there because the gas is being collected. So there is bubbling. It's actually pretty slow. I should have started timing just now. I have to start timing the moment I added them in. But humans, very difficult to multitask, okay? Very, very difficult to multitask. Some experiments will ask you to count the bubbles. Some experiment will just ask you to actually record the volume of the gas after a fixed time. By right, again, I should have started timing the moment I added in the acid, but human being human, your hand control one acid, the amount of acid that you're adding from the measuring cylinder. Your other hand controls the airtight rubber band that you put on top of the gas collection apparatus, this one here. So you don't have another hand to click the stopwatch and start the experiment. So sometimes what students do is they just start timing first, and then they put the stopwatch on the table. They start timing, they put the stopwatch on the table. When the stopwatch read like 10 seconds, then they put in everything. Then their final result, they will minus 10 seconds from their final result, because they know that they can't do everything in one go, because they only have two hands. Then the result will be more accurate if they take away the time later on, because they only added in the stuff at 10 seconds. Regardless, the time is still going, but you could see the rate of production, the rate of reaction is pretty slow. The volume of water has come down because the gas that is being produced passed through the delivery tube, and the gas fill up the space. Just now it started from 0. Now it's about 10, around 15 cm cube. So what I'm going to do is I'm going to record the volume of gas produced in 2 minutes. So this is minute, this is second. In 1 minute, there is 60 seconds. So when you have 2 minutes and 0 seconds, there will be 2 minutes times 60, which gives you 120 seconds. I'll stop timing at 2 minutes, and then I will record the volume of the gas at 2 minutes. Okay, so it's getting close. So gas will still be produced, but I will stop reading at 2 minutes. So there's 15, 16, 17. So I'm just going to remove that, and then I will bring that closer. Let me see. Can I bring it closer? Maybe, maybe not. So there's 0. There's 0, there's 10. And then there is 15, 16, 17, 18. 18 cm cube in 2 minutes. You got 18 cm cube of gas in 2 minutes. The thing at the very end there is just a very accurate seconds, but you read to the nearest second, which is 0. So 2 minutes, 0 second. There's 2 minutes times 60. There's 120 seconds, and you produce 18 cm cube of carbon dioxide gas. All right. So I'm gonna restart this experiment now, but with the crushed powder. So I'm gonna remove that. So our reaction is not complete yet. How do I know the reaction is not complete yet? As you could see, there is still bubbling, there is still fizziness. So the gas is still being produced because you see bubbling, you see bubbles, you see effervescence, you see bubbling. It's just it's very slow, and I only record the volume of gas after a fixed time. So I remove that. So this is now a clean conical flask, no more acid in there. What I do then is, this is my 2 grams of the crushed solid. So I'm just going to scoop out the whole thing in there. So by using the same mass of the solid, the same concentration of the acid, because we are only investigating surface area of the solid, so surface area is what we are changing, and we are not changing any other factor. In this experiment, the things that you don't change at all, you keep them the same in the 2 experiments. They are what you call control variable. Control variables means you don't change these factors, but they could affect your reaction. So the powder stuff are inside. Just now, I use hydrochloric acid. I use 10 milliliter, so I'm going to use the exact same volume. So the volume of the acid, the concentration of the acid remain the same. I should probably redo my measuring cylinder displacement. So I'm going to show you how to do it again. I will fill up my measuring cylinder with water. So fill it up to the very top with water. And then what I do next is, I close the top, I hold it with my hand, put it all the way in there, do not let go until it is submerged in the water. If you let go, all the water will come out. Then lift it up a little bit, because you want to have the inlet at the bottom for you to put the delivery tube. So remember that we could potentially start timing, and then if I start timing, oops, where am I? Nope. I need to get this to work. Oh, no. If I start timing, and then I leave this on the, if I start timing, and then I leave this on the bench, when it reaches 10 seconds, then I leave this on the bench, and when I reach 10 seconds, I will pour in the acid and close it, and then there will be a more accurate result actually. So perhaps that is what I should do here, okay? I will get this set up first. So this is the delivery tube. So I'll pocket underneath here. So this one reads 0 cm cube at the very beginning. This is now 0.00. I'm just going to start timing first. And then when you reach 10 seconds, what I'll do is I will hold one hand, hold the rubber bunk, and then this one. As you could see, very rapid, very rapidly. As you could see just now, the bubble, very rapidly, all the way suddenly is already there. You could see the rate of bubbling is a lot faster compared to just now. And you can see there's a lot of volume of gas produced. You need to take away the 10 seconds, so I'll stop timing at 2 minutes, 10 seconds. I believe that this reaction might produce a lot more gas than that. So my measuring cylinder might not be enough. So I haven't done an exact calculation of the amount of gas I should get, but this should give you an idea that the powdered form reacts so much faster. Look at what happened in the conical flask. So the conical flask, almost all the solid is gone. If you look carefully, almost all the solid is gone. There is still bubbling because there is still gas being produced. Not only the bubbles are there, but the bubbles are also on the measuring cylinder here. So the gas is being produced a bit slower now. It was really fast at the beginning. Suddenly the volume dropped a lot, but now it's getting very slow, but there is still bubbling. It's just very slow now. what you could do is you should have swirl the conical flask. Swirling means you give it a bit of a swirl, and then you will see what happened to the bubbling here in the measuring cylinder. So if I give it a bit of a swirl, you can see the bubbling is a lot faster because you're actually ensuring that all the solids are exposed to as much of the acid as possible. So what is the time now? I don't stop at 2 minutes. I should stop at 2 minutes 10 seconds because just now I started timing and then I left it on the bench, and then at 10 seconds then I put in everything. So I'm going to read the volume at 210. Okay, so let's see, it's nearly 210 now, so 210, I take this out, and now I'm ready to record the volume. If I don't take that out, it is continuously producing gas and it will not be accurate at all. So your volume has been displaced from there, 0, all the way to there. Here, let me see if I can make you see the reading a bit better. I don't think you will be able to see the reading that well, but I can try. So what does it read here? This is 70, this is 80, this is 80, this is 90, 91, 92, 93. So in 2 minutes, because I took away 10 seconds, in 2 minutes, 93 centimeter cube. Just now the lumpy form, in 2 minutes, you only get 18 cm cube. So in just the time taken, okay, so let me just zoom out that thing there, and let's just recap back on what we have learned. So we know that the lumpy form will react a lot slower because in the same time it produces a lot lesser gas. This gas that you are producing is actually carbon dioxide gas. Carbon dioxide gas is a gas that you get when metal carbonate reacts with acid. So metal carbonate reacts with acid to give you metal salt, and also carbon dioxide gas and water. So here the lumpy form reacts a lot slower compared to the powdered crushed form because the crushed form has a much bigger surface area. So your point of contact with the acid, with the reactants is a lot bigger. Bigger surface area results in faster rate of reaction. So the time taken to collect a fixed volume will be shorter. But here we are measuring the time taken, we're measuring the volume of the gas produced in a fixed time, and we could see there's a lot more volume of gas being produced in that fixed time from the powdered form. Here, the reaction here was basically the acid plus the carbonate. So what I'll do is I have this thing called lime water. So lime water is used to test for carbon dioxide. Lime water is this colorless solution, lime water solution. So lime water plus carbon dioxide will give you a white precipitate, a white solid, a cloudy, milky precipitate. So this reaction produces carbon dioxide. Instead of collecting the gas, I will bubble the gas through this thing here. So I have lime water in there. So this is just my lime water, it's colorless solution. I will put some more acid into here. Remember just now this was the remaining carbonate. I put in some more hydrochloric acid. Do I get any reactions? I still see bubbles, so there is still gas being produced. I close it up. The gas that's being produced is basically carbon dioxide. Look what happened to the lime water. The lime water slowly turns cloudy. The lime water slowly turns milky. Just now it was colorless solution. The gas is bubbling. The gas is colorless, but what you see is you bubble the gas through lime water. And what happened to the lime water? The lime water turns milky or cloudy. Just now it was colorless, lime water. Lime water is used to test for carbon dioxide. This reaction between a metal carbonate and an acid, it bubbles the gas. It doesn't bubble the white precipitate because look, this thing is not connected to the bottom. It's the gas that passed through the delivery tube. And what do you see now? The lime water gives you a white solid, or it gives you a cloudy precipitate because this test is for lime water. So to summarize, the test for the test for carbon dioxide is using lime water. Lime water plus carbon dioxide give you calcium carbonate because lime water is calcium hydroxide. Lime water is calcium hydroxide, Ca2 plus OH minus. Calcium hydroxide or lime water plus carbon dioxide give you a cloudy or milky or white precipitate of calcium carbonate, which is insoluble in water. Okay? That's it really for this tutorial video. I've done tests for carbon dioxide, but the majority of the lecture experimental tutorial was actually investigating the effect of surface area, the powdered form versus the lumpy form. The lumpy form has a smaller surface area, the powdered form has a greater surface area. Rate of reaction increases as you increase surface area from the lumpy form to the powdered form. Okay, thank you for watching. Don't forget to click the button on the bottom right on my channel to subscribe to my channel. Follow me at ptet.chemistry on Facebook, Instagram, Twitter, and Telegram to get connected. I'll see you in the next tutorial video. Thank you for watching again.